Welcome to video number 8 in Advanced Fluid Mechanics. So in this video, we're going to be starting section number 5, which is called Boundary Layers and Related Topics. And this is also going to be the last section we're covering in this Advanced Fluid Mechanics course. So we're going to be covering what's shown in the white text here in this video, and in the next one we'll do the gray text. And so essentially, we're going to be looking at boundary layers, which is a thin layer that forms as fluids flow around objects where we have viscous effects. So in this video, we're going to look at what they are, different ways to describe them, and then some different ways how you can solve for the fluid flow behavior within these little boundary layers. All right, so let's get started. Okay, so let's first talk about what boundary layers are and what do we use them for. So until the beginning of the 20th century, they were able to get analytical solutions of steady flows for basically two different situations. One of them is what we've already seen back in section 4, where you have parallel viscous flows and low Reynolds number flows, where those nonlinear advective terms were zero, okay? And basically the forces that were balancing there were pressure forces and the viscous forces. And the second type are inviscid flows, so the opposite, right? So instead of the viscous terms dominating, we don't have those viscous terms in the equation. And these were around bodies of various shapes, where instead the balance of forces is between the inertial forces and the pressure forces. Now you might be thinking that still included those nonlinear terms in our momentum equation, but you can actually get the velocity field by solving the linear Laplace equation. And what they found was for this second set, these irrotational solutions that they found actually were able to predict pressure forces around these streamlined bodies really effectively. Okay, so those match the experimental data, but the solutions predicted zero drag force and a non-zero tangential velocity, which we can think of as like slip at the surface. And that did not agree with what the experiments were showing. Okay, so we needed some way to rectify that. So actually in 1905, Ludwig Prandtl, and I really like this story because he's actually an engineer, so he was motivated to find the realistic fields near these bodies, right, with these different shapes. And so what he figured out, right, was for these small viscosity situations, the viscous forces are negligible everywhere in the flow, right? So these inviscid flow solutions, except really close to our solid boundaries, okay, where we'd have to satisfy the no slip condition. So basically then you think of it as like there's two different zones, right? There's the inviscid flow like farther away from the body, but then we make this little boundary layer, right? This really thin boundary layer right around the object. And in there, the viscous forces are actually really important, okay? And so he was able to satisfy these two things, right? Like the effects of viscosity are actually negligible in most of the flow field, right? But he was able to also account for the fact that there is drag on these objects, right? By making sure that we satisfy the no slip condition right at the wall. So it's actually quite brilliant. So that's how we end up with this boundary layer. And then what we're gonna do is look at this boundary layer itself, talk about how we use it, how it helps us, okay? We're gonna look at the equations of motions within the boundary layer, okay? And see how they can be simplified to a way that we can solve them. We'll look at approximate methods of solving them too. And then we're gonna, of course, the whole point of this was to get the drag right on these objects. So we're also gonna take a look at how we get the drag on the objects in this section as well. Okay, so in section 5.1, let's talk about the boundary layer approximation. And we'll see that because our layer is very thin, we can simplify the equations of motions within the boundary layer. And so we can see from this picture here, we're looking at airflow over an airfoil. And out here, it's labeled as irrotational flow. So that's where we can solve an inviscid flow. So the viscous effects aren't important. But right here within, we're showing this dashed line where the boundary layer is, right? So right there, you can see how the velocity changes so much. So the viscous forces are important because we have the no slip condition right against the wall. And the velocity increases out to that, what we call free stream velocity, which is our capital U there, okay? Now a note in this figure, the boundary layer thickness is greatly exaggerated in this picture just so we can see it and visualize it and I can talk about it. It's not this big at all. So for example, around a typical like airplane wing of full size, it would be roughly a centimeter thick, right? So it's actually quite thin. So we're gonna be considering the case of a boundary layer that's next to a wall. We're gonna use a curvilinear boundary layer coordinate system. So X is gonna be considered along the surface, like shown here, and Y is gonna be normal to the surface, shown like that. And we're gonna call this irrotational flow in the inviscid part, like farther away from the wall. We'll call that the outer problem, and I'm gonna refer to the flow within the boundary layer as the inner problem. Now, as is shown in the figure here, the thickness of the boundary layer varies with X, okay? And some of this you might have seen in an undergraduate level fluid mechanics course. You know, for example, I do cover the basics of boundary layers in my undergraduate fluid mechanics course, so I'll put a link to the video where I cover that up here. But we're gonna be diving into this with a lot more detail here in advanced fluid mechanics. So we're labeling this delta here, probably time to switch to another color. Maybe I'll go with green. So this delta right here as the thickness of our boundary layer. And anytime I'll write delta with a bar over it, that's the average thickness of the boundary layer over the length of the body. Okay, so that's like this delta with the bar over it shown right there. Now we can figure out approximately how thick this delta is going to be by doing our consideration of the order of magnitude in these terms in the equations of motion. This is something we've done before as well, right? It's like a scaling analysis. So I'm showing here this equation. So this is the steady equation of motion for the longitudinal component of velocity, right? Our u velocity, because that's in our x direction, right? Along this object. And this Cartesian form where we have this x and y, it's only valid where we don't have a massive curvature, right? So that's where the boundary layer thickness divided by r, which is our local radius of curvature of the body shape function, right? So that has to be much, much less than 1. Okay, so generally that's going to be small for large Reynolds number flows over slender shapes. And in this equation, we've also neglected body forces, and we haven't considered any variations of density and viscosity, because we're just want to focus here on the features of our viscous boundary layers, okay, without considering all these other things. So we're just going to look at that for this problem. Okay, now we're going to look for our characteristic magnitudes, right? So for u, we have our u infinity in the flow field here, right? It's also known as our free stream velocity sometimes, or we would call that the upstream velocity at large distances away from the body. We need a length scale L, where it's going to be a distance over which u changes appreciably. We can scale by this L that we have here, a length scale of our problem, because our lowercase u velocity within the boundary layer does change by a large fraction of u infinity over our distance L, right? So we can look down here now, right? So if you have this velocity profile here, and then along this distance L, right, we have this second profile down here, and you can see that the velocity within the boundary layer at a certain distance away from the surface, right, which is shown with these arrows here. I'll trace over them as well. So this arrow here, and then down here we have this arrow here, and so you can see that's changed by approximately the scale of u infinity over this distance L, right? So that will serve as our good scaling distance, capital L there. So you should be taking notes here. Of course, I can write a few as well. So we'll say like our characteristic scaling. So we have u that can scale like u infinity. L, right, is going to be our distance over which u changes by that scale u infinity. We could then say that u, right, by x scales therefore like u infinity over L. So our first term here, right, would end up having a scaling that would be approximately like u infinity squared over L. The viscous term here will scale like, we usually use this to say that it's of the order. So that will be like this. And we use delta bar as the characteristic length in our y direction, which is the average boundary layer thickness. So to find the scaling of our boundary layer thickness, the argument we make is that this advective term here, right, and the viscous terms that are over here, like this one, for example, that we've looked at, they have to be roughly the same order of magnitude within the boundary layer if the viscous terms are to be important, right? So then comparing these two expressions that we just have with our scaling here and here, okay, we rearrange that to see that then our boundary layer thickness, or average boundary layer thickness with the bar over it there, is approximately this. Or we can recognize, we can write that another way with some terms we're familiar with. It's the order of 1 over square root of our Reynolds number. Okay, there's a few other ways to get this term as well, but I think this demonstrates it really nicely. Okay, so now that we know roughly how thick the boundary layer is, right, in terms of order of magnitude, we're going to move on now and simplify the equations of motion within the boundary layer. And we're going to use this basic idea that like any changes in the x direction for our velocity are going to be much, much smaller than these changes in the y direction. Okay, so we're saying like, for example, when the velocity from here to here is going to change versus the velocity as you look along the y direction, which is right here, right? So these changes in the y direction, moving away from the surface, are going to be much larger than variations along the surface of the body. Okay, so anytime we have any differentials in x, they're going to be much, much smaller than any of those within y. The y ones are going to be dominating here, right? Moving normal to our surface. Because the distances in the x direction over which the velocity changes are of order L, right? It's capital L. But in the y direction, they're of order delta, which is our boundary layer thickness, and that is much, 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 much smaller than L, right? And again, we can look at our scaling here. If I put a little box around it, right, that can emphasize that as well. We just figured that out, right? Because Reynolds numbers are fairly large in these flows. So delta is always going to be substantially smaller than capital L is, right? Now we're going to look at how our v velocity varies within the boundary layer. For this, I will use a different color because I'm getting a little tight of space already. We're going to consider the continuity equation. Now we know that u is much, much larger than v is here. And as we mentioned, our changes in x are much, much less than our changes in y. So those two things should somewhat balance off, and therefore the two terms in the continuity equation should roughly be of the same order, okay? And so what that's gonna give us is it gonna mean that u infinity over L is gonna be approximately the same order of magnitude as this v over this delta. Okay, and so that I'll write up here because there's a little more room. So we'll simplify and see that our v, our velocity in the y direction, is approximately then, when we rearrange, it's like this, which again we can rearrange to be related to our Reynolds number, plugging in for our delta bar there. So we can see our velocity in the y direction is of the order of our u infinity divided by the square root of the Reynolds number. One more thing before we move on and simplify our equations here is to look at the magnitude of our pressure variation within the boundary layer. Now, from experimental data, we actually know that in these high Reynolds number flows, the pressure distribution in the boundary layer is nearly the same as that in the irrotational flow around the body, implying that the pressure forces are about the same as the inertial forces. So then from our equation, comparing like this grouping here to this grouping here, which I'll use a dark blue for that, okay, and say that those are of the same order, we would therefore have this, I'll show it like over here, same order as like this term. Therefore, the pressure variations approximately scale like density times u infinity squared. And therefore, finally, time for a fresh slide. When we remember, like, we have this scaling here that we've come up with for v, we have our pressure scaling here, our boundary layer thickness we've scaled like this, changes in x versus changes in y we've looked at on here. We'll put all this together and we're gonna get our non-dimensional variables, and I'll do that on a fresh slide so we can actually see what's going on here as we move to simplify the equations of motion within this boundary layer here. Okay, so these are the non-dimensional variables we have from all these scalings that we just talked about. So x, for example, will scale in L. I've shown this figure here again so we remember. Y scales to our delta bar, which is our average boundary layer thickness. We sub in for delta, which we remember on the previous slide, like this. Okay. U scales with u infinity. B we looked at as well, scaled like this, and then pressure, we did the pressure scaling on the previous slide as well. So that's all of them there listed in their non-dimensional form. Now we sub all that into the equations of motion for the boundary layer. Okay, and this is how we're going to simplify them, right? By looking at these scaling. Just make it really clear too here that the Reynolds number we have defined in this case as this grouping here, like an overall Reynolds number for this boundary layer. Okay, now because of our scaling arguments, each term in these equations is order 1 because we've normalized them all. So for example, like when you look at this term here, that's roughly order 1 because the changes in these u prime and y prime variables within the boundary layer are each of order 1, right? Now you see we have this multiplying factor of Reynolds number for many of the terms in these equations. So for example, like looking at this equation right here, right? Each of these terms is order 1 except for this one here, right? That has this multiplication of the Reynolds parameter. So that's going to have a magnitude of order 1 over Reynolds. Okay. Now, as Reynolds approaches infinity, becomes really large, the equations asymptotically become the following shown down here, right? Because like this term goes to 0 as Reynolds becomes large. So does this grouping, right? We can see anytime they're multiplied, those ones there as well. So you're only left with certain terms. Now this non-dimensionalization has been really valuable for us, right? Because it showed us which terms drop out under our boundary layer assumptions. So we can transform these back to dimensional variables. And that's what we have in the box down here. It's already boxed, but why not box it again? So this is what we end up with for our approximate equations of motion within the boundary layer. Okay. Now we'll look at a few consequences of this. So if we look at this middle equation right here, right? That one's interesting, right? Because it tells us the pressure is approximately uniform across the boundary layer, right? Because it's saying di p di y equals 0, which means that the change in pressure over the y direction is 0. So the pressure at the surface is roughly equal to that at the edge of the boundary. Okay, so we can actually find the pressure from solving this irrotational problem that we talked about before, that inviscid problem that's valid further away from the body. Okay, and what we do there is we say that pressure is imposed on the boundary layer by the outer flow. Okay, and this of course helps to explain why in these experiments the measured surface pressure was correct, right? It matched what they had calculated when they did those inviscid solutions from that what we'll call irrotational flow theory. Okay, and just to note that we have made some approximations, so there are going to be cases where you may have P changing in the y direction, right? We'll see later, we'll talk about boundary layer separation, okay, where you're going to have in that case a different pressure on the surface because the boundary layer separates from the wall in that case. Or if the curvature is too high, right? Because we assumed we had low curvature in this problem. But for the most part, we're going to have no change in pressure across the boundary layer in the y direction. So normal to the surface, right? And we can use, I'll write it actually here just for completeness, the pressure gradient at the edge of the boundary layer. We can use the inviscid Euler equation for that. Put a subscript E on those U's to denote edge. So that's the velocity at the edge of the boundary layer. And at the edge, we could eliminate the velocity in the y direction, so our lowercase v term, because at the edge of the boundary, it scales roughly like 1 over square root of Reynolds number, which goes to 0. Okay, so we don't have to consider that. So that's why the equation simplifies to this form. Okay, so that's just an equation we can use then to solve for the pressure gradient. Now, we don't actually have to use it to find dpdx at the edge of the boundary layer. You can actually, as a first approximation, use it to solve along the surface of the body and neglect the existence of the boundary layer. Okay, because the error goes to 0 as the boundary layer is really thin, and we've seen that approximation already works very well. Okay, so you solve that outer problem first, right? And then you'll get that dp dx term from that solution of the outer problem, right? We have the following boundary conditions that we use to solve these equations of motion. So maybe I'll highlight each of these in turn. We should recognize these by now. So this is basically for all x at y equals 0, our u velocity is 0. So that's saying we have no slip because the solid boundary is not moving, right? So the flow against that solid boundary can't be moving either. We have no flow through the solid boundary itself, right? So the v velocity is 0 at the surface as well. We're imposing by this one the fact that the boundary layer must join smoothly with the inviscid outer flow. So points outside the boundary layer are represented by this like y equals infinity, although essentially we're referring to this non-dimensional distance y over delta scales like this here that we've written, which approaches infinity outside the boundary layer. And our final condition that we've listed there implies that we need some initial velocity profile, so this in, this u sub in, at some location x naught is required to solve this problem. And that's because we have these terms here, this one and this one here, that will end up giving the boundary layer equations a parabolic character. So x is sort of like playing the role of a time-like variable, which actually is similar to that suddenly accelerated plate that we solved back in section 4, right? Where it was like di u by di t equals nu, and then the second order differential of di u di y. These problems, they're governed by parabolic equations. So the field at a certain time or the field at a certain x in the problem here depends only on its past history. Okay, so boundary layers therefore transfer their effects only in the downstream direction, right? Whereas the Navier-Stokes equations, they're what we call elliptic. And elliptic equations require specification on the bounding surface of the domain of the solution. So the Navier-Stokes equations are elliptic in velocity, and therefore they require boundary conditions on the velocity or a derivative normal to the boundary, upstream, downstream, and on the top and bottom boundaries. So like all around the domain, right? And so the upstream influence of these downstream boundary conditions is of concern in the computations. So in summary for this one here, to solve the equations of motion within the boundary layer, this full set here, we would need to have some initial velocity profile at some location x naught. And so just to summarize what we've accomplished here in simplifying these equations, basically because the layer was so thin, we were able to make the following simplifications. Okay, so first we saw that diffusion in the x direction is negligible compared to that in the y direction. Okay, we saw that the pressure field can be found from the irrotational flow theory. So we consider that as a known quantity in our boundary layer analysis because it comes from the solution of the outer problem, right? Because the boundary layer is so thin that the pressure doesn't change across it. That's what we saw from our analysis here. We could actually do one more thing as well. So we can make a rough estimate of the shear stress at the wall, or the skin friction, because we now know the order of our boundary layer thickness. Okay, so our shear stress at the wall, we know that scales like mu du dy, right? From Newton's theory. So that's roughly gonna scale like this, which we can plug in for because we have some of these scalings now. So that is actually this scaling here. Okay, so our skin friction coefficient, then we can sub this in right here, which I've written out already. And that gives us a rough idea, right, of the magnitude of the skin friction we're going to calculate. So not an absolute value, but that gives us an idea of what we're expecting for our skin friction. And we'll actually see from some solutions that we're going to do that this is indeed the correct order of magnitude for scaling this, right? So our analysis is actually effective here. It's working. And only the finite numerical factor will differ from problem to problem. Otherwise, the scaling is correct. Okay, so that boundary layer approximation is really powerful, okay? And we're able to get a lot of information about the flow within the boundary layer here. So next we're gonna move on and look at different measures or different ways to classify our boundary layer thickness. All right, so section 5.2, different measures of boundary layer thickness. I've decided to include this here for completeness, but I am assuming that you covered this in your undergraduate level fluid mechanics. So we're just gonna go through this quickly, not in a lot of detail, because we have honestly a lot cooler things to look at in advanced fluid mechanics here. So I don't need to be repetitive. And again, I have the link to the video in my undergraduate fluid mechanics videos where I cover this. So you can check that out there as well. We'll just go through this pretty quickly, and I've listed here on the slides the information from the textbook itself, and we're going to reference this a little bit as we go forward. So I'll just cover it again very quickly here. So we have basically three ways, right? So we have what's called the U equals 0.99 U thickness, okay? And that essentially is just saying that one way to measure the thickness of a boundary layer is that you could decide it ends at the point where the velocity is 99% of what the free stream velocity value is, okay? And as is mentioned here, that's somewhat arbitrary to pick, right? We also have what's known as the displacement thickness, okay? And that's saying, like, best to sort of see this from the figures here, that's saying if you had a frictionless flow, right? So if you had the velocity profile not influenced, so if it was straight, right, like it's shown in this one here, okay? That's saying the distance away from the wall that would have to be displaced in order to make up for the fact that you have less mass flux, right? So we see, like, down here, there's less mass flux because the velocity is slower near the boundary, okay? So then that distance here, right, says that that's how far away from the surface you would have to be to make up for the mass flux that you had from the velocity being slower. Okay, so they've listed the equations here, right? The resulting equation down here for how you calculate that. And that one's not arbitrary, right? So we can use that as a more, let's say, exact way to sort of quantify boundary layer thicknesses, right? As is mentioned here too, you can read through this as well. They could use that in the design of ducts or wind tunnels by assuming a frictionless flow and then enlarging the passage by the distance you would need to make up, right, for the fact that there is this viscous effect near a surface. Or to find dp dx at the edge of a boundary. Okay, so lots of different uses of this. And this figure down here at the right shows another cool way this can be interpreted. It actually shows that when you have these streamlines shown here, this delta star, right, which is what we call our displacement thickness, delta star is how we're labeling it. It actually shows that the streamlines are displaced by this distance, delta star, see right here, due to the presence of the boundary layer being there. Okay, so that's another kind of cool and helpful way to think of it, right? Now we've got one more. I've got that on another slide. So this one's called the momentum thickness, and that's denoted by this theta here, and that's very similar to the displacement thickness, except instead of the mass flux that's reduced by the lower velocity near the surface, this is actually considering the momentum loss that's due to the presence of the boundary layer, okay? And so we have our equation because of that. Sections A and B referring to the figure. So you have the momentum loss like this, substituting what we had for the displacement thickness, and you end up with this one right here. Okay, so basically just three different ways of measuring the thickness of a boundary layer, okay, by looking at different ways like it influences the flow at a certain distance away from a surface. All right. Okay, so next we're going to look at the classic problem of a boundary layer on a semi-infinite flat plate. Okay, so we've already come up with these equations. We did that in section 5.1, and we're going to use these because they're a valid asymptotic representation of our full Navier-Stokes equations in the limit Reynolds approaching infinity. Okay, now for this flat plate, our inviscid solution, like the outer problem, tells us that u equals constant free stream velocity everywhere, and di p by di x equals 0. Okay, so we can simplify those equations that we came up with earlier into this form I've listed here. Now we're also going to consider that the plate length L, capital L, is actually so big that we're going to find a solution that's independent of this L, okay? And also, we're going to only consider a domain that's far downstream of this X naught condition, right? So you remember we talked about that other condition we had to satisfy. So if we're far enough away from X naught, the initial condition has been forgotten, okay? And so now we're going to find a solution to these that's a similarity solution, okay? So we have no externally imposed length scale in that X direction, okay? So therefore, as we've seen previously, right, now the solutions at various downstream locations must be self-similar because we don't have that length scale to scale to, right? So it was Blasius, who was a student of Prandtl, who showed that a similarity solution can be found for this problem. And that can only happen, so they'll only collapse into a single curve if the solution has the following form. So we scale u like this. That would have to be a function of this eta term, where eta is our y direction scaled with the boundary layer thickness. And now we can stop and compare this to the last similarity solution that we did, which was that suddenly accelerated plate that we did back in section 4, where we did have similarity solutions, okay? And in that case, we argued that the capital U parameter drops out of the equations if we scaled the velocity lowercase u over u and considered that as the dependent variable. And then we had that was a function of y and time and our nu. And our dimensional analysis showed that we had that functional form u over u equals, and then we had capital F was a function of y over delta. So in our current problem, the downstream distance is time-like, as we mentioned before, but we can't make our functionality like x and y in nu, okay? Because we don't have a time variable, right? So nu cannot be made non-dimensional by just using x and y, okay? So we couldn't scale it that way, right? Because we're missing the time variable. And the basis for this is the fact that we can't sort of eliminate this capital U from the problem just by scaling the velocity to u, because actually delta, like our boundary layer thickness, actually still depends on u. So it remains in the problem that way. So basically what we're gonna have is we'll have a solution of the form like this. Where delta is a function of u and x and nu, and therefore delta has to scale like this, right? That's the only grouping we can find for that. Okay, so now we're on a quest for a similarity solution, right? For our flat plate boundary layer. Okay, the problem is 2D again, so we can find a stream function, right? We remember again, the stream function satisfies our continuity equation, right? So it's this. Because subbing that in would solve our continuity equation, right? In 2D, Cartesian form. Okay, and then using that, we can get the following. Integrate from 0 to y of u. Basically separating and integrating, right? And then I can sub in for this. Where that's an eta there, in case I didn't quite write it neatly enough, we're subbing in from above, right? So to be really clear, like you can sub this into there to get this one, and then sub this in there to get this one, and finally that will be this, where we have defined this g function b df d eta. So therefore, similarity form of our stream function is this. Just sort of rearranging that. which tells us that the scale for the stream function is proportional to the local flow rate, u times delta. Okay, now we're gonna sub in to these equations here. Okay, so this one's like right up here, right? When we sub it all in, continuity was already satisfied, of course. And these are subject to the following conditions. So like at the surface, right? We have the no slip condition. So u is 0 at y equals 0. And as we approach infinity here, right? U approaches our free stream velocity. Now we want to further simplify for our similarity stream function f, right? So we can go ahead and sub that in down here, right? So I show how each of these terms can be written in terms of f, which we've got right here. And anytime we have these primes here on these terms, that denotes derivatives with respect to eta. Okay, so when you go ahead and sub all of that in, right, those are all the simplifications. You sub that into here, you get this expression right here. Okay, now let's look at how we solve for that. Okay, so I got a fresh slide here. I've got our equation that we just came up with right here by subbing everything in, and we can see that f and its derivatives don't explicitly depend on x, right? So this equation can only be valid if this term right here is a constant. So we'll write that out here. Now what we're going to do is we're going to choose this constant to be a half, and that's just because later on that's going to give us algebraic simplicity. And we'll see, so if we assume that constant is a half, separate and integrate, we're going to end up with this right here. We sub in for our original equation, subbing in half as our constant and rearranging, moving terms all over to one side of the equation. We're going to have this following here. Right, that was just this equation, okay, rearranged, and we sub in a half for that. And in terms of f, we'll have the following boundary conditions. So f prime at infinity equals 1, f at 0 equals f prime at 0 equals 0, because f was equal to our stream function over u times delta. Okay, so this is a nonlinear function then that we're solving for right here. So Blasius came up with a series solution for this that was subject to these conditions right here. Nowadays, we can solve the problem with a computer. Of course, we can use techniques like the Runge-Kutta method. A resulting profile we're going to have, right? So we're going to have u over u equals f prime eta, right? That's shown down here in this figure at the bottom. And so you can see the profiles at our various downstream distances collapse into a single curve of u over u versus this eta parameter here. And it agrees really well with the experimental data we have for laminar flows at high Reynolds numbers. Laminar meaning the flow within the boundary layers laminar. But our free stream velocity can have high Reynolds numbers. Okay, so that's kind of awesome, right? That's our solution to the flow within our boundary layer, right? That's awesome. Now our transverse velocity we can solve for as well, right? So that's the velocity in the y direction. So moving normal to the surface, because v is negative psi x, which I've shown down here. So therefore we can sub in because we have our velocity profile now. So then we can simplify and rearrange for our v velocity, or transverse velocity, using our solution that we've come up with. So we simplify for v here. Therefore v over u can be represented like this. And that simplifies to this approx solution, 0.86 over Reynolds x. As our eta approaches infinity, there's a plot for this, right, where we have 0.86 as eta gets very big. And so v times root Reynolds over u. We can plot against our eta, and our transverse velocity we see goes from 0 at the wall, which we know because it's a solid wall, to a maximum at the edge of the boundary layer, okay, which matches the streamline shapes that we would expect. We can solve for the boundary layer thickness as well, right? So we have our 99% one, our displacement thickness, and our momentum thickness. The expressions for those are given there. We'll note that the local Reynolds number here that's referred to as like Reynolds sub x is defined as free stream velocity times the x location along our flat plate, right, divided by nu. We see a prediction of parabolic growth, right? So this boundary layer thickness is a function of root x in each of these cases, right? And that's in good agreement with experiments as well. If you wanted to just sub in some numbers too, as a reference point here, for example, for air at ordinary temperatures flowing at a velocity of 1 meters per second, meaning our capital U is 1 meters per second, the Reynolds number at a distance 1 meter from the leading edge of our flat plate would be 6 times 10 to the 4. And this equation here for our 99% boundary layer thickness would give a thickness of 2 centimeters in that case, right? So 1 meter away from our leading edge, we would only have a boundary layer of 2 centimeters. So it shows that it is in fact fairly thin, and that gives us a sense for just how thick we're talking about here. These are also shown, interestingly, the displacement and momentum thickness are shown on the figure right here. Okay, so that's where they would be in that case. It's kind of a neat reference point, right? We can look at our skin friction as well. One of the most important things of this analysis, right, that we wanted to figure out. Okay, and our local wall shear stress, I'll write this out here, as given again by Newton, is this. Subscript 0 is for y equals 0. And then we can sub in for the stream function. We solved for this on the previous slide, so we go ahead and sub in. And then finally that leads to this expression right here. You note again the functionality, so the wall shear stress decreases as x to the negative a half in this expression, and that's a result of the thickening of the boundary layer and associated decrease of the velocity gradient, right, which our shear stress is of course a function of our velocity gradient. But of course the wall shear stress at the leading edge from this expression would be predicted to be infinite, and so clearly our boundary layer theory does not work near that leading edge, where the assumption that the changes in the x direction are like way smaller than changes in the y direction, so that makes it invalid, right? So you wouldn't use this expression, of course, to describe the conditions right near the leading edge, right, which is like right at the front part of the flat plate where the boundary layer begins to form. And the local Reynolds number near that leading edge is of order 1, which means that our boundary layer assumptions were not valid for that point anyways, right? We can also express this wall shear stress in terms of the non-dimensional skin friction coefficient. Okay, and then I've shown again, because I knew I would probably run out of space if I wrote this by hand. So that skin friction coefficient, right, could be, we could scale the wall shear stress like this, and that would give us this expression here for our skin friction coefficient. We can also go ahead and get the drag force on one side of a plate that had a length L, okay, by integrating, right, from 0 to L, that wall shear stress. That would give us this expression right here. In that case, just to note, I'll do it right here. From this case, Reynolds number based on the plate length would be defined, of course, this way, just make it explicit. That equation actually shows that the drag force is proportional to the 3/2 power of velocity. And this we can compare actually to the low Reynolds number flows where the drag was proportional to the first power of velocity, right? We write the overall drag coefficient, right? So we scale that. I'm showing that on the bottom right here, as we normally do to get this expression like that. It's also clear that a comparison between our overall drag coefficient and our skin friction coefficient, right, would have the following relationship shown right here, which says that the overall drag coefficient is actually the average of the local friction coefficient, which makes sense. And again, we have to keep in mind that like we're integrating from x equals 0, right, to L, but that might not have validity because the equations and the solutions are only valid for very large numbers of this Reynolds X condition, right? So we just have to keep that in mind when looking at these drag conditions. And then this plot here shows this comparison, right? So we see that the overall drag coefficient, right, is the average of the skin friction coefficient. The plot actually shows that really well, okay, at this distance L, that would be at our average value. So that's a way to kind of visually see it. Okay, and that was pretty awesome, right? So we actually solved the equations of motion within the boundary layer, right, for this flat plate scenario. And that gave us a whole bunch of information about this boundary layer, the skin friction, the thickness, and all of that, right? So really valuable analysis there for a fairly simplified case of this. Okay, now in section 5.4, we're gonna look at the Falkner-Skan solution of the laminar boundary layer equations. And this is a similarity solution as well that actually includes the Blasius solution, but it's even more general. Okay, so this refers to the work of Falkner and Skan in 1931, where they found that if we express the velocity at the edge of the boundary layer like this, that leads to a similarity solution. And our Reynolds number would then be this. And for this, we would have to assume that it's sufficiently large that our boundary layer equations are valid and any dependence on an initial condition has been forgotten, similar to what we said for the Blasius solution that we just looked at. So our initial station x0 disappears from the problem, and we can write it like this, like I've shown right here. I haven't showed all the steps again, but I'll just remind you, we can go about this the same way we did previously. So for our stream function, u is this, and v is this. And you follow the same steps as we did before, right? So you integrate those and you get the functionality of our stream function here, because the stream function, of course, has to satisfy our continuity equation. And then we would have the following. and this u edge velocity times du e by dx would equal this. So now when we would sub that in, our x momentum equation reduces to the similarity form I've listed right here. And rather than rewriting everything, so again, that's referring to the x momentum equation that we used previously, same as the Blasius solution, right? And then we would have the conditions listed here. And now we can see from this expression actually that the Blasius equation is a special case for n equals 0, where the u edge velocity would be equal to u, capital U, the free stream velocity. And then we're not concerned with the n less than 0 solutions because they're not likely to be seen in practice. So for n greater than and equal to 0, the solutions to these equations have the proper behavior. Then our numerical coefficients depend on n. So I'm showing in this figure here solutions to these equations for different values of n. And so one interesting thing to note, if we look right here, we see the shear stress, which is represented at f double prime at 0, increases monotonically as n increases, right? Increasing values of n go this way, right? And then for this case right here, n is negative 0.0904. This f double prime 0 right there actually equals 0. Okay, so then the wall shear stress equals 0. And what that means actually is separation is imminent all along the surface. And we're gonna look at separation in more detail in the next video. Just for now, we just note that solutions for n less than this negative 0.0904 don't represent boundary layers. And in most real flows, the similarity solutions are not available. And then the boundary layer equations with boundary and initial conditions that we wrote earlier, that whole set must be solved. Okay, so here we're just looking at the cases where we can have similarity solutions because it tells us a lot of interesting things about what's going on in the boundary layer, right? So oftentimes what you have to do with this set of boundary layer equations, because they're so complicated, is you have to solve them numerically. So it ends up that they need to be integrated numerically to solve them. But we also, at the end of this video here, we're going to look at a simple approximate procedure that's called the von Karman momentum integral. Right now, though, we're going to have a discussion about how these laminar solutions break down. Okay, so what happens is when our boundary layer is nice and laminar, the Blasius solution agrees with our experimental data. But this agreement breaks down for large downstream distances where the local Reynolds number, which I'll write here so we have a reminder of that, ux over nu. So that breaks down where the local Reynolds number is larger than some critical value, right? And this Reynolds critical for a flat plate is approximately equal to 10 to the 6. And what happens is at these Reynolds numbers, the laminar flow becomes unstable. And so there's a transition actually to turbulence, right? So from a laminar boundary layer to a turbulent boundary layer, right? So the flow within the boundary layer becomes turbulent. This critical Reynolds number varies a lot with things like the surface roughness, the existing fluctuations on the problem. So like how steady the flow is within the outer irrotational flow, the shape of the leading edge. And so in those cases, it would actually make it a little lower than this critical number, 10 to the 6 here, but this tends to be a good approximation. And this picture actually shows what's going on, right? And so basically for a finite value of this, so this Reynolds number approximately equal to 1, okay, you're gonna need the full Navier-Stokes equations to describe the leading edge region properly, right? So you gotta solve the whole thing. And then as this local Reynolds X value gets large, we can locate this X naught value, shown right there, as the maximal upstream extent of the boundary layer equations. Okay, so beyond this point, our laminar boundary layer equations are valid. Now, for some distance, we do need the initial condition at x naught, like we talked about when we came up with the equations, right? Because that's going to be remembered for some distance. But then eventually, the influence of that initial condition can be neglected, and then we can find the solution in the similarity form, like we did. That's basically shown as like being kind of like down in this zone right here, right? And then as our local Reynolds number, REX, continues to increase and we go farther downstream, our first instability appears. And then as it increases, the flow becomes increasingly chaotic and irregular in the downstream condition, which we tend to call transition zone, going like from our nice organized laminar flow into our turbulent flow. And then it becomes fully turbulent with actually a significant jump in shear stress at the plate, tau 0, right? So we notice a significant increase in our shear stress value. After transition, so if we look right here, right, the boundary layer thickness grows faster than x to the half, and the wall shear stress increases faster with u than in the laminar boundary layer. In contrast, the wall shear stress for the laminar boundary layer varies as tau naught is proportional to u to the 1.5 exponent. And this increase in resistance is due to the greater macroscopic mixing that's present in a turbulent flow. Now, this, of course, is also going to result in a different drag force, which ultimately is really what we're concerned about, right, when we talk about boundary layers. And this variation of the drag coefficient can be expressed as a function of the Reynolds number. So I've got got this other plot shown here, so we can see how this changes. Drag coefficient plotted against our Reynolds number. So we've got the laminar one down here, right? We got what we'll sort of call this transitional zone here. That applies if the boundary layer is laminar and then turbulent over the remaining part. And then we've got where it's fully turbulent, right? It's shown as this top line right here. Now, of course, where it becomes transitional really depends on your experimental conditions. This one's shown at about like 5 times 10 to the 5 here. But that'll really depend on your conditions. Okay, now let's look at one more way we have to solve the boundary layer equations. Okay, so in section 5.6, we're gonna look at the von Karman momentum integral. So exact solutions for the boundary layer equations are possible only in simple cases, like the one we just did for the case over a flat plate. In more complicated problems though, one way we can do this is to see if we can find an approximate solution, right? So an approximate method will satisfy only an integral of the boundary layer equations across the layer thickness. And basically the point of that is that we wanna find the information that we really care about with minimum effort, okay? And these, in this case, are, for example, the wall shear stress, the displacement thickness, and the separation point, okay? So this integral was derived by von Karman in 1921, and with the help of the von Karman momentum integral that we're gonna derive here and some additional correlations, we can get these important results that we care about for our boundary layers. Okay, so we start with the boundary layer equation that I've listed here, and we're gonna integrate that from y equals 0 to y equals h, where h greater than delta is any distance outside of the boundary layer. And here what I've done is I've substituted for this pressure gradient term and rewritten it in terms of the velocity at the edge of the boundary layer where the inviscid-Euler equation applies so that we get this term right here. Okay, so that's the substitution we described earlier. Then what we do is we add and subtract u du dx. Okay, to get this line here. Okay, and then we integrate from y equals 0 to h. We show one term at a time, so right, so that's this term here. For the first term, integrating by parts, the third term is this one here, where we can also use the continuity equation to further simplify these, and the conditions that v equals 0 at y equals 0, and u equals capital U at y equals h, which makes this term equal 0. The last term here is done up here. Okay, and I've shown all the detail here, so if you want, you can take some time with this and make sure you can follow each of these steps here. And so what we have then is the integral of this expression here is this one here. When we sub all those in, then we see we can simplify for this integral. So we solve that right here, and we end up with this expression right here, where this theta is the momentum thickness that we defined earlier, right? That's why I wanted to show it to you. And we had the displacement thickness show up earlier in this term too. And therefore we sub all that in, we get this, which is already boxed, but I'll box it again. Anyways, we get this expression right here. And that's called the Karman momentum integral equation, where we have the displacement thickness from here, momentum thickness from here, and our wall shear stress from here. And those are all unknown. So additional assumptions must be made or correlations provided to obtain a useful solution. It's actually valid for both laminar and turbulent boundary layers. For the turbulent cases, our wall shear stress can't be equated to the molecular viscosity times the velocity gradient, and that actually has to be empirically specified. And essentially the procedure of applying this approach is to assume some kind of reasonable velocity distribution that satisfies as many conditions as possible. And then this equation will predict the boundary layer thickness and other parameters. Because remember, we said this was an approximate method, right? So you can actually see it's pretty powerful. So generally what you would do is you would apply this where you don't have exact solutions available. But just to kind of show you how powerful this is, what I'm going to do now is apply it to the boundary layer over a flat plate, which we've already solved for, so we can compare to that. So I'll do that on another slide here. Okay, so we're going to apply this to the boundary layer over a flat plate. So we know in that case that u dx term equals 0. No change in our free stream velocity, right? So we got rid of the second term, and then what we do is we apply this here as the definition for our momentum thickness being subbed back in. And I've included a picture of the bottom right-hand corner from the previous slide to just remind you what our final equation was and the substitution that we made just right there on the line above it. So that simplifies our equation to this. Then what we can do, right, we mentioned is we're going to assume a velocity profile. So let's assume a cubic profile for our velocity, like shown like this here, okay? We'll satisfy our 4 conditions. So we mentioned we want to satisfy our conditions with our velocity profile. So no slip at the wall, at y equals delta, we have our u equal our free stream velocity. So we have no more change in u in the y direction at that free stream condition as well. And at the wall, we're also going to say our second order differential in the y direction is equal to 0. And that comes about because at the wall, that's a requirement in a boundary layer over a flat plate. Because if we look at the equation of motion, when u du dx equals 0, the term that's nu times this second order differential also has to be 0. Okay, so that's where we got that expression from, which is this one right here. I'm actually showing the complete definition of each of these steps here so that you can follow along with them as well. So then we get the constants with these boundary conditions, right? The profile simplifies to this one here. So then we can go ahead and sub that in to our equation up here to get this right here. And when that is subbed into there, those terms, we end up with this expression right here. We can then separate and integrate, right? So we integrate in x using the condition delta equals 0 at x equals 0, right? Because that's right where our boundary layer starts. We get this right here. And this is extremely close to the exact solution, right? This expression here, which we remember in that case, that coefficient was actually 4.9. versus this 4.64 that we got here. So that's pretty good, right? And then the friction factor, if we use this to sub in for that, we end up with this expression right here, which is also very close. The exact solution that's mentioned here, remember? Previously, we got that to be 0.664, so also very, very close, right? So for an approximate solution, that's pretty good, right? With, basically minimal effort, we were able to get extremely close to these solutions that we got from the exact solution. And so it shows you how in cases where, of course, we don't have an exact solution, where this is really valuable, okay, we can apply this and get pretty good understanding of what's going on there. And so you see there's a lot you can do with this, especially when you take different forms of the velocity profile that you're going to start with here. So it's actually a really powerful method. Okay, so we're going to stop there for video number 8, and we're now partway through section 5. So just as a quick summary, what we did is we talked about the boundary layer approximation, why we need it, right? Because the solutions we had previously didn't consider flow very close to the boundaries of objects, and so we weren't really able to predict the drag force very well or satisfy the no slip condition. So with this fairly simple approximation, now we can get all kinds of information that we need about flow around objects. And so then we looked at different ways to measure the boundary layer thickness, which is this thin layer that we assume around these objects where the viscous effects matter. And then we looked at how do you solve the flows within these boundary layers, right? So we could then get an understanding of the flow behavior close to these objects and therefore understand ultimately the drag force or the skin friction. We looked at when these laminar solutions break down. And then finally, we just finished here with the von Karman momentum integral, which showed an approximate solution for this versus the similarity solutions that we used earlier for the exact solutions. Okay, so that's all for video number 8. Thanks for watching.